Students, today we are going to discuss the monostable multivibrator. Now initially, to start with the topic, let's discuss about the monostable multivibrator, that what is a multivibrator at first and then what is a monostable multivibrator. Now as in electronics, there are oscillators. You all know what is an oscillator. An oscillator is a amplifier circuit with a positive feedback. Now every oscillator, there are two types of oscillators. Number one is the oscillators which produce a sinusoidal waveform, and there are some oscillators which does not produce sinusoidal oscillations, and those are known as the relaxation oscillator or the multivibrator. So multivibrator circuits are essentially oscillator circuits, but those oscillator circuits may produce, or rather those oscillator circuits always produce non-sinusoidal waveforms. So in short, we can say that a multivibrator is nothing but a non-sinusoidal oscillator or a non-sinusoidal waveform generator. Is it okay? So let's dive into what is a monostable multivibrator. In multivibrator circuits, we usually find there are three types of multivibrators. I think you all know about that. These are monostable, bistable and astable multivibrators. Now astable, starting from an astable multivibrator, astable means a multivibrator which has got no stable states. No stable states are known as an astable multivibrator. That means for an astable multivibrators, the waveforms we can find from those circuits are usually not stable. So these are also called free running oscillators, or rather free running multivibrators. Now next, the bistable multivibrator. What are the bistable? Bi means two. So a multivibrator circuit which has got two stable states. Two stable states, they may be on or off. So there are two stable states. You can find that in a flip-flop circuit there are also two states, high and low. So a flip-flop is also known as a bistable multivibrator circuit. So in a bistable multivibrator circuit, the waveforms we found, there are two stable states, high and low. Now interestingly, monostable multivibrator, mono means one. So a multivibrator circuit which has got only one stable state. Only one stable state is a monostable multivibrator. Now you can find that, or you can tell me that how would it possible that a waveform has always, as we know that a waveform, if it is non-sinusoidal, that waveform must possess two states, either a high or a low, a high or low. So there are two states, but as I am telling you that a monostable multivibrator has got only one stable state, so how can the waveform is formed? Actually, here in this monostable multivibrator circuit, we also get a waveform, and that waveform has also a high and a low. But these high and low, there is only one stable state, and the other state, it may be high or it may be the low state, is an unstable state. So a monostable multivibrator has only one stable state, and the other state is not a stable state, but it is known as a quasi-stable state. Okay. So this is the story of a monostable multivibrator. So we already came across what is a multivibrator and what is a monostable multivibrator. Now as I told you that a monostable multivibrator has one stable state and the other is a not stable state, or rather that is a quasi-stable state. Now these two states, that is either a high or a low, can be treated as the stable state, Similarly, a high or a low can be stated as the unstable state or the quasi-stable state for a monostable multivibrator, which state, that is whether the high or the low is the stable or the unstable state, it actually depends on the circuit configuration. Okay, so here in this particular lecture we are going to discuss, or we are going to construct a monostable multivibrator by using 555 timer circuit. In our previous day class or in our previous lecture, we already came across the operation, the internal configuration or the internal structure circuit of a 555 timer. Now again, going back to the monostable multivibrator topic, that a monostable multivibrator has a stable state. It is already defined, or it is already told. Now for transition, or to make a transition from the stable to the unstable, or from the stable to the quasi-stable state, this multivibrator circuit requires a trigger. That is a pulse which is required to make the transition of this multivibrator circuit or of this monostable multivibrator circuit to go or to transit from the stable to the quasi-stable, or from the stable to the unstable state. And after reaching the unstable state, actually the waveform or the wave gives a width of its waveform, and that width of the waveform is already or is going to be discussed later on in this lecture. And that if you will see that this width of the pulse is actually determined by the external components used in this circuit. So now let's move on to discuss how we can construct a monostable multivibrator circuit by using a 555 timer. Okay? Any question right now? Have you any questions? Have you any questions? Or just give a thumbs up. Give a thumbs up to. Okay, Masud give me a thumbs up. Thank you, Masud. Anybody have any queries till now? Okay, Shinjini, Najrul. Okay, sir. So let's move on to, okay, Udar, fine. So let's move on to discuss about the circuit or about the monostable multivibrator by using the 555 timer. Now recalling our previous lecture, or some points, 2 points of our previous day lecture. Now yesterday or in our last class, last lecture on 555 timer, what we have explained or what we have get from that particular lecture, there are 2 points to discuss in our yesterday or in our previous lecture. Those points are to get a high output. To get a high output from the 555 timer, we have to apply a voltage which is actually less than 1/3 VCC, and that will give the trigger comparator output. High. So that was point number 1. Okay, so to get a high output at the 555 timer output, or to get a high at the 555 timer, we have to apply a voltage at the trigger input trigger input of the 555 timer so that the trigger comparator goes below the 1/3 VCC value, that is to get a high at the 555 timer output. And number 2, that to get a low at the 555 timer output, we have to apply a voltage at the threshold input of the 555 timer so that the threshold comparator output goes high. So that the threshold comparator output goes high, and which results in a low output at the 555 timer. So these are the 2 points to remember right now to start this topic. Is it okay? Remember these 2 points we already discussed in our last lecture on 555 timer. That is, there are 2 possible ways or 2 points to remember. The points are: number 1, to get a high output at the 555 timer, the trigger input voltage should be low than the value 1/3 VCC, and which will tends or which will actually gives the 555 timer output a high. And to get a low output at the 555 timer, we have to apply a voltage at the threshold input pin, so that the threshold comparator at the threshold input pin just high above the value of 2/3 VCC, which results in the threshold comparator goes high, and then the output of the 555 timer goes low. So these are the 2 points to remember, or rather these are the 2 points on which our particular lecture, that is the lecture or topic on monostable multivibrator, depends. Okay? So here to discuss about the monostable multivibrator, let's start the topic with the first point. That is, we are going to apply a voltage at the trigger input which actually is less than 1/3 VCC value, and that will result in the trigger comparator goes high, and which actually gives a high output at the 555 timer. So this is the voltage which is required, and that is the trigger input. Now remember again that the trigger input value should be less than the 1/3 VCC. Now let's look at this picture. So this is the trigger input. That is the input, or that is the pin number 2, and as you can see that this is a negative going pulse. So this pulse actually makes the trigger input value less than 1/3 VCC. So this is the trigger input, or this is the value of the input voltage which we are going to apply at the trigger input of the 555 timer, so that the output of the 555 timer goes high. Okay? Is it okay? So we are actually going to discuss this monostable multivibrator circuit by regarding or by considering the trigger input voltage. So trigger input voltage is necessary, as I have already discussed, that for a monostable multivibrator to switching its states from the stable to the unstable, or from the unstable to the stable state, a trigger input is required, and this trigger input is actually make the trigger input voltage value less than 1/3 VCC, which actually makes the output of the 555 timer goes high. Okay. So now let's discuss about the stable state first. And later on we move on to discuss the quasi-stable state. So starting from the stable state, or how to get the stable state of the monostable multivibrator circuit. So let's move on to discuss about the stable state first. Now here in this figure, you can see that when the power is switched on, before any trigger input. So let's forget about the trigger input at first. So when the power is switched on, the capacitor C will try to be charged through R towards the value VCC. So at first don't bother about the trigger input value. First discuss just now, if we are start or initiate the circuit switch on the circuit, what happens? This capacitor, here you can see a capacitor. This capacitor and this resistor is actually an external, these are the external components of the circuit to be used. Now as the circuit is switched on, this capacitor sees or finds the value of VCC. This capacitor finds the value of VCC, and if we initially assume that the capacitor is discharged at time t equals to 0, then after switching on the circuit, this capacitor will tend to charge through this resistor R towards the value of VCC. So the capacitor voltage, which is, we assume that if the value of the voltage is initially at 0, then the capacitor will charge. Then the capacitor will be charged and it goes on to have the value of VCC via this resistor R. Okay, so now till now we are not going to discuss the effect of this trigger voltage, or now we are not going to apply this trigger voltage till now. Okay. Okay. So step number 1, that while the circuit is switched on, or when the circuit is switched on, if we have no voltage applied at the trigger input, then initially the capacitor tries to charge. The capacitor tries to charge to the value of VCC via the resistor R. Now here again, just look at this picture again, and you will find that this capacitor is also shorted, or is also connected with pin number 6. And what is this pin number 6? It is the threshold pin. And right now, in start of this particular lecture, I have already tell you, or rather in our last lecture, we have already discussed that when the threshold value, or when the threshold input voltage is higher than 2/3 VCC, when the threshold input voltage is higher than 2/3 VCC, then the threshold comparator goes high. Now consider that while charging the capacitor, if the capacitor is initially discharged, that is if the capacitor voltage is 0 at time t equals to 0, and then after switching on the circuit, the capacitor tries to charge itself, that is the charge inside the capacitor goes on increasing, that is it starts from 0 and it will end for the value of 5 volts. Now as it go on increasing its value, that is while it is charged, then 0, then after 0.5, 1, 1.5, 1.7, then 2, 2.5, and then after crossing the value of 3.3, or rather 3.5, that is the 2/3 VCC value. 2/3 VCC is actually 10 by 3, that is 3.33, around 3.33 volts of value. Now as the capacitor has got, or as the capacitor crosses the voltage value of 2/3 VCC, that when the capacitor reaches the value of say 3.5 volts, what will happen? What will happen? In our last class, we already discussed that while the threshold input is higher than the 2/3 VCC value, then the upper comparator or the threshold comparator or comparator 1 goes high. So now as the capacitor has a value of voltage higher than 2/3 VCC, then the threshold comparator or the threshold pin has got a higher value of 2/3 VCC, and that results in the threshold comparator goes high. So the threshold comparator goes high, which means that the R input, reset input of the RS flip-flop goes high. So the R input or the reset input of the RS flip-flop goes high. We already discussed in our last lecture that while the threshold comparator goes high, it will make a high at the R input of the RS flip-flop, which actually resets the flip-flop. That means the Q value of the flip-flop goes low. The Q value of the flip-flop goes low. That means the Q bar value is equals to 1, and that is after crossing the output buffer, it will be at 0 value. So while the capacitor has a value higher than 2/3 VCC, while the capacitor, again I am repeating again to make yourself easier to familiarize with this particular topic, that if the capacitor is charging and then after reaching the value of 2/3 VCC, as this capacitor is connected to this particular point, that is pin number 6, which is the threshold pin. So the threshold pin goes above the value of 2/3 VCC, which actually make a reset input goes high for the RS flip-flop inside the 555 timer, which actually makes a low at the output of the 555 timer. So now till now we have arrived at a low value at the 555 timer output. So have you got it till now? Is there any problem? Is it okay? So what we are discussing, we are actually discussing about the stable state of the monostable multivibrator, and here we consider that we have not applied the trigger input right now. We have not applied the trigger input whatsoever and just switch on the circuit. To switch on the circuit, this capacitor actually goes to charge to the value of VCC via this resistor R. And now when it goes on charging, one certain time will be there when the capacitor value crosses the value of 2/3 VCC, that it will cross the value of around 3.5 volts. And when this capacitor voltage is around 2/3 VCC, then as this capacitor is connected to the threshold input, that is the pin number 6, that will make the threshold comparator goes high. And if the threshold comparator goes high, that means the R input, that is the reset input of the RS flip-flop internal to this 555 timer block, it will goes high, and when the RS flip-flop goes high, the Q output of the flip-flop will be low, which actually makes Q bar equals to 1, and the output of the comparator goes low. Now, so the comparator output goes low. Till this is okay. Now, since Q bar equals to 1, now now this Q bar, as in our previous lecture I have shown you, you may remember that this Q bar is actually connected with the transistor or the discharge transistor Q1. This Q bar is actually connected to the base of the Q1 transistor, and the collector of the Q1 transistor is connected to pin number 7. So this is the discharge pin. You might remember this is the discharge pin, that is pin number 7. So now when Q bar equals to high, we have already discussed in our previous lecture that when Q bar equals to high, then the transistor Q1 will be in saturation, and as the transistor is in its saturation state, then the pin number 7 or the discharge pin, which is connected to the collector input of this Q1 transistor, this discharge pin goes to the value of ground. This discharge pin or the current through this discharge pin will flow towards the transistor, and through the transistor this current goes to ground. Okay, so that is the point we already discussed in our last lecture. Now recall here now what we have in our pin number 7. Pin number 7 is also connected to the capacitor, and right now we are discussing about the value of the capacitor voltage at around 3.5 volts, that is greater than 2/3 VCC value. So while the capacitor goes on, if the value goes on a value higher than the 2/3 VCC, then the threshold comparator goes high. While the threshold comparator is high, the reset or the R input of the RS flip-flop goes high, which turns the output of the flip-flop goes low. That means Q bar is high, which actually makes the transistor Q1 in saturation state, and that saturation state actually makes the discharge pin goes to ground value or goes to a very low value, about 0.2 volts, as because the VCE saturation value is not right now is not 0, but it is closely 0, that is around 0.2 volts. So while the capacitor has got a value of 2/3 VCC, that is around 3.5 volts, so now this value of the capacitor will go to make a 0, will be discharged. So that means the capacitor, while we are discussing about the charging of the capacitor, actually the charging of the capacitor makes the capacitor discharge. So while charging the capacitor, when it goes beyond the value of 2/3 VCC, it now discharges. So this capacitor value will be in 0 state, will be again goes to 0. Is it okay? Why the capacitor goes to have a value of 0 volts? You should be understand why this capacitor value is 0. And actually this is this stable state of this particular monostable multivibrator. So for this monostable multivibrator, what is the stable state? The stable state is a low. The stable state is a 0 value, and this 0 value occurs as because while you are switching on the circuit, to while you have switched on the circuit, this capacitor, if this capacitor is initially at a value of 0 volts, it goes on charging as this capacitor is connected to the VCC via this resistor R, and as it goes on charging, it will certainly cross a value of around 3.5 volts, and as sooner this value of the capacitor goes beyond the 3.4 or 3.5 volts, then the threshold comparator goes high, which actually makes the output of the 555 timer low, and as the output of the 555 timer goes low, the Q bar of the RS flip-flop goes high, which actually makes the discharge transistor in its saturation state, and this actually results in pin number 7 goes to ground. Pin number 7 goes to ground, which implies that this value of the capacitor or the capacitor has a path to move towards the 0 value, and that is the value we are discussing, that the capacitor value will be 0, and it will be 0 in its stable state. So lowering the value or the low value of the monostable multivibrator, that is a 0 value at the output, is actually the stable state for the monostable multivibrator. So already, if you all understand, so already we have came across about the stable state for this monostable multivibrator. Is it okay? Give a thumbs up. I think if you understand this way, you will find a simplified explanation, and this will help you to remember. So have you find it interesting right now? Till now is it interesting? Okay, so you all find it okay. So let's move on to discuss about the unstable state. So right now we have not applied the trigger input. We have already discussed to just by ignoring the trigger input or the trigger input value equals to 0, we have already discussed. So we have switched on the multivibrator circuit, and we find that the circuit is at its stable state, and that is nothing but a 0. So now we have to got a waveform. Actually, what makes sense, that to get a 0 value at the output, it will not certainly make a sense. So now we are interested to make this 0, to make this low value to high. So to make this low value towards a high value, we have to apply a trigger input. And what is the trigger input? Already I have discussed, and the trigger input is nothing but a negative going pulse. A negative going pulse which makes the trigger input voltage value, that is at pin number 2, the trigger input value less than or smaller than the 1/3 VCC value. So right now we are going to apply that particular negative going pulse, a negative going pulse which makes the trigger input terminal value less than 1/3 VCC. Okay? So when the trigger pin of the timer is forced to go below 1/3 VCC using a negative going pulse, what happens? What happens? We have already discussed in our yesterday or in our last class that when the trigger input goes low or goes low below 1/3 VCC, that means the S input, that means the S input of the RS flip-flop, the S input of the RS flip-flop goes high. When the trigger input goes below the value of 1/3 VCC, when the trigger input goes below the value of 1/3 VCC, the trigger comparator goes high. The trigger comparator goes high, and where this output will go, the trigger comparator output is connected to the S input or the set input of the SR flip-flop. So the set input will go high. And now if the set input of the SR flip-flop goes high, which actually makes the SR output goes high. So the SR output goes high. Actually that will make the Q bar of the SR flip-flop output goes low. Again, I am recalling the entire part. That is, now we have applied a trigger voltage. That is a negative going pulse. Remember, that is a negative going pulse. So it will make the trigger input voltage value goes below the value of 1/3 VCC. Now whenever the trigger input goes below 1/3 VCC, then the trigger comparator goes high. And as the trigger comparator output is connected with the set input of the SR flip-flop, that means the set input of the SR flip-flop goes high. And as we all know from the truth table of a SR flip-flop, that while S equals to 1 and R equals to 0, it will make the Q output of the SR flip-flop goes high. So right now the Q output of the SR flip-flop will be at its value of high, and that will make the Q bar of the flip-flop goes low, and as a result the output, the final output of the 555 timer goes high. Now as because the Q bar is low, and as this Q bar is connected to the base of the discharge transistor or the base of the Q1 transistor, so the Q1 transistor will be in cutoff state. The Q1 transistor will be in cutoff state, and as a result no current will flow from the pin number 7 to the transistor. And that's why we called it in our last class also, we called it that the discharge pin is actually disconnected, right? So the discharge pin is actually disconnected as because there will be no current flowing through the discharge pin to the transistor Q1, as because the Q1 transistor is in cutoff state. Now what is the value of this pin number 7 right now? What is the value of pin number 7? Right now the value of the pin number 7 is 0. The value of the pin number 7 is 0 as because the capacitor is discharged, because the low output value of the 555 timer is nothing but the stable state of the monostable multivibrator, and as a result the capacitor is always in its zero state. The value of the capacitor voltage is 0. Now as this pin is disconnected, virtually disconnected, we have already discussed that this word is virtually disconnected. As this pin number 7 or the discharge pin is virtually disconnected from the discharge transistor internal to the 555 timer, what happens? then the capacitor again finds the value of VCC, then the capacitor C again finds the value of VCC, and it again goes on to charging. It goes on to charging, or it goes on to have a value from 0 to 5 volts. So that is the charging path, but this charging path has a resistor, as I have already discussed. So by having a value of this resistor R, the capacitor goes on charging right now, as because the discharge pin is disconnected from the discharge transistor, or the capacitor finds the value of VCC, so the capacitor now starts to charge again. And the capacitor, what I have already discussed, that this charging time, that the capacitor C goes to charge through the resistor R towards VCC with a time constant of RC. Okay? Is it okay? So initially at the first part of this particular topic, we have discussed the stable state. And we have find that zero value at the output. Zero value at the 555 timer output is its stable state. And as the 555 timer output is 0, so that means Q bar, that is the output of the flip-flop, SR flip-flop, is high. That will make the discharge transistor in its saturation state, which actually makes the capacitor value goes to ground. That was the discussion about the stable state. Now after completing this stable state, now we have applied a trigger input, and that is nothing but a negative going pulse, which decreases the trigger input value, beyond the 1/3 VCC mark, 1/3 VCC value. And as the trigger input goes below the 1/3 VCC value, the trigger comparator goes high. I am repeating to have a simplified picture of this monostable multivibrator. So as the trigger comparator goes high, the trigger comparator output is connected to the set input of the SR flip-flop. So the flip-flop output, that is the Q output, is high. That means Q bar is low, and the final output of the 555 timer is high. You just remember that the value of the 555 timer is high. Now as Q bar is low, it will make the transistor Q1 in its cutoff state. So that means pin number 7, that is the discharge transistor. So no current will flow, allow to flow or to pass through the Q1 transistor, as the Q1 transistor is at its cutoff state. That means now what is the voltage value at pin number 7? The pin number 7 is connected to the capacitor itself, and the capacitor value is right now 0, as because the 555 timer is low, always at its stable state. So now this capacitor is disconnected. The capacitor is disconnected from the circuit, or that is actually virtually disconnected, not actually disconnected. But as the capacitor is virtually disconnected from the discharge pin, now it will again find the value of VCC. So again the capacitor starts charging. And now the time constant is RC. As because the capacitor has found a resistor in its path of charging. Is it okay? So that is the unstable state. As this is the unstable state, so the output which actually goes high, so the output which actually goes high will always make shift to the stable state of this 555 timer or the monostable multivibrator, that is nothing but a 0. So it was initially at the value of 0, and that is the stable state value, and now after applying the trigger input, the output of the monostable multivibrator goes to high, and certainly it will come down to 0 again. It will come down to 0 again, and that will require no trigger voltage value. How it will be possible? So now again you consider now the capacitor is go on charging. Now the capacitor is go on charging, so the value of the capacitor is now increases from 0 towards VCC or towards the value of 5 volts. Now after crossing again the value of 3.4 or 3.5, that is the 2/3 VCC, again the similar things happen. That is the threshold comparator goes above the 2/3 VCC value, which will again make the threshold comparator goes high, and that will reset the RS flip-flop output, that the output will be 0. That means Q bar is high, and as Q bar is high, that will make the Q1 transistor again in its saturation state, and then the pin number 7, that is the discharge transistor, find a path to move on to have a value of 0 volts. That means now the capacitor value, which is nearly around 3.4, 3.5 values, it will certainly go on to discharge, and it will go on to have a value of 0 volts. So this is a cycle. I have already discussed about the entire cycle. Initially I will start to discuss that when the capacitor is at the value of 0, how it will go on to have a value of 3.4, 3.5, and then again it will shift to a value of 0 volts. So this is the entire stable state of operation. Now after the stable state of operation discussed, I have applied a trigger value which will certainly make the output of the monostable multivibrator goes high, and then you will find that now again the capacitor starts to charge. So now the capacitor again starts to charge at the quasi-stable state, and then only after reaching the value of 2/3 VCC, it will certainly go on to discharge and have a value of 0. So that is the entire operational explanation. Is it okay? Have you understand the entire topic? Any doubts? No doubts. Okay. So I am just now going to draw the waveforms. I think it will help you to find it more simplified. So let's draw first. At first, I am going to draw the trigger input valve. As this is a negative going pulse, so this is the negative going pulse. Okay, let this value is about VCC by 3. So I am plotting the trigger input. Here the trigger input is plotted. So you will find that the trigger input, this is the negative going pulse. This is the negative going pulse. Is it okay? Can you all see the graph here? That is the trigger input graph. Now, as the trigger input graph is important to us, it is also important to have the value of trigger comparator. So now this is the graph of the trigger comparator. Now, as the trigger input goes low, so this is the negative going pulse. This is the negative going pulse, and as this negative going pulse appears, it will actually make the trigger comparator. It will make the trigger comparator goes high. So it will, what I have discussed, what I have explained, I am showing it in its waveform. So the trigger comparator goes high. So the trigger comparator goes high, and that will make the capacitor. Now I am going to draw the capacitor waveform. So this is the capacitor value. Now, as the trigger comparator goes high, what will happen? The trigger comparator goes high, which actually makes the output, of the flip-flop high, That means Q bar is low. And that means the capacitor have a value to charge, have a path to charge towards the VCC value. So the capacitor charging is initiated when the trigger comparator goes high. Now, so that at this particular point, as the trigger comparator goes high, the capacitor goes to charge. Now, if this is the value of VCC, this is the value of VCC, so the capacitor will go to charge this way. So the capacitor will start to charge from 0 to VCC. Now, as we have already found that it will never reaches or never touches the value of VCC, as because when the capacitor value is about 2/3 of VCC, when the capacitor value is about 2/3 of VCC, it will make the threshold comparator goes high. It will make the threshold comparator goes high, and that is the point where the capacitor again starts to discharge or have a value of 0 volts. So the capacitor actually can move on to have a value of 2/3 VCC. Maximum it can have a value of 2/3 VCC. So after reaching the value of 2/3 VCC, the capacitor will start to discharge. So this is the point from which the capacitor goes to discharge its value. Okay, so this is the VCC, this is the capacitor voltage value. Now, when this is, what is the value of the threshold comparator output? Now I am drawing the threshold comparator output. As the capacitor, so I mark these points. Now, as the capacitor starts to discharge, as the capacitor goes from 2/3 VCC to 0, then the threshold comparator have a value high. So then the threshold comparator goes to high. So here the capacitor value crosses or touches the VCC, 2/3 VCC point, then the threshold comparator goes to high. Just the threshold comparator value, this threshold comparator goes to high. Now what it sends? It makes the value of Q bar. Now I am going to draw the value of Q bar. Now as the threshold as the trigger comparator goes high, so this will make Q bar low. And because when the threshold comparator goes high, then the reset input of the RS flip flop goes high. When the threshold comparator goes high, the reset pin goes high, and that will make Q equals to 0. Certainly Q bar will be high. So here the Q bar value will be high. Now lastly I am showing you the output pulse. That is the important part. So that is the output pulse. So what happened that when the Q bar is high, that makes the output pulse goes low, and when the Q bar is low, that will actually make the output pulse high. So this is the part where the Q bar is high, and this is the width of the pulse TW. So this is the width of the pulse TW for which the output pulse, or for which the output of the monostable multivibrator goes high. Right? Have you find it? Have you understand these all graphs? What I have talked to you, what I have explained to you verbally, I have drawn here all the things. I have drawn the trigger input, then the trigger comparator output, then the capacitor value. When the trigger comparator goes high, when the trigger comparator output goes high, the capacitor starts to charge. The capacitor starts to charge from 0 value, and when it reaches the value of 2/3 VCC, it will goes to discharge again, and at the point of 2/3 VCC value, the threshold comparator output is high. As the threshold comparator output goes high, the capacitor goes on discharging. Okay, so that is the time I have drawn the Q bar value, and as you can find that while the trigger comparator is low, Q bar is high. As the trigger comparator high makes the set input high, which actually makes a high at the output of the 555 timer, and as a result Q bar is low. So here, while the trigger comparator output is high, the Q bar output is low. And as the Q bar output is low, it makes the output pulse high. And the pulse width is represented by TW. Is it okay for you all to understand? Now from this timing diagram, it is proven, or it is evident, that the pulse width TW depends on the time of charging. So as the capacitor charges, this is actually the width of the pulse. this is actually the width of the pulse, or this is the value of TW. So it is evident that the value of TW only depends on the charging of the capacitor. Okay, this only depends on the charging or the time of charging of the capacitor from 0 to 2/3 VCC, which actually depends on the time constant RC of the circuit, or the value of RC which is connected externally with this monostable multivibrator circuit. Okay? Is it okay? Okay. Now lastly, a small explanation is required. Now we are going to find out the value of TW. So what is the value of this width, that is TW? So now we are going to calculate the value of TW, and to get this value calculated, we are going to use the general formula for charging and discharging of capacitor with time. That is, as we know, the general expression for the charging and discharging of a capacitor, that is VCT. That is the charging or discharging time, and that is equals to the final value VF plus VI minus VF into e to the power minus T by RC. So this is the general expression. This is the general expression of charging and discharging of a capacitor. So we are going to use this expression where VI is the initial voltage of the capacitor at time t equals to 0, and VF is the target voltage to which the capacitor tends to charge. So VF is the target voltage at which the capacitor tends to charge, that is VF equals to VCT at t equals to infinity. If time t equals to infinity, then the value of the capacitor voltage is actually VF, or the final value. Now for this circuit at time t equals to 0, the capacitor value is VI equals to 0. And at t equals to infinity, what is the target value of the capacitor voltage? The target value of the capacitor voltage is VCC. So the target value of the capacitor voltage is VCC. So here we are going to, let's remove this. Let's remove this also. So just remember that here to calculate the value of TW, we actually depends on this capacitor waveform. So the capacitor starts charging from 0 value, that is the VI value. So let's at first mention these values, that is VI equals to 0 at t equals to 0. The target value, that is VF, will be 5 volts, or VCC, that is at t equals to infinity. But what we find in this circuit, that the capacitor voltage, it will be 2/3 VCC, and then it will starts to discharge. It will starts to discharge. So that is the value of VCT. That is, at any time t, the capacitor value may have a value of 2/3 VCC, and that is the value of the pulse width. So that is at t equals to TW. Okay, so these are the three values. These are the three values we have to incorporate, or we have to substitute in this expression. So let's find how we can do it. So using this expression, VCT, that means VC, and T means TW, and that is 2/3 of VCC. So 2/3 of VCC, that will equals to final value VF, that is VCC, plus VI, that means 0, VF means again VCC, then e to the power minus TW by RC, as the time constant here in this circuit is nothing but RC. So here we have 2/3 VCC, 2/3 VCC, that equals to VCC minus VCC e to the power minus TW by RC. Okay, so let's make VCC common, that is 1 minus e to the power minus of TW by RC. Here and the left hand side 2/3 of VCC, so VCC cancels, that makes e to the power minus of TW by RC equals to 1 minus 2/3, that means 1/3. That means 1/3. So here we can find that the value of TW, we can find the value of TW equals to RC ln 3, as because here a negative sign appears, so making use of the logarithm we can find the value of TW equals to RC ln 3, and as we know the value of ln 3 is around 1.1, so the simplified value of the width of the TW is 1.1 RC, is 1.1 RC. Okay, so if we have the value, or if we are interested enough to have a pulse width for a monostable multivibrator predetermined time, for a predetermined time, if we want to make this value of TW, or if we have a value of TW at first, then putting the value of TW and selecting any value for the capacitor, we can find out from this expression the value of R to be used in the circuit, and that is the way we actually construct a monostable multivibrator in practical by using the values of R and C, and by using this particular expression of TW equals to 1.1 RC. This is the most simplified form. This is the most simplified form of the expression, that is the value of TW. And initially when we are going to have our practical classes, if happen, then we have to construct a monostable multivibrator circuit. In our question we always asked, or we always have a value of TW given. So having a value of TW at first in our hand, we just consider to have a value of capacitor in the circuit at first, and then from this particular expression we just find out the value of R to be used, and then this simple circuit to be constructed, having those values of R and C. Having those values of R and C, only two components are required, and also here a particular fixed value of capacitor is to be used at the terminal number or the pin number 5. Okay, and then after giving a negative pulse, then just giving a negative pulse, we have a waveform. We have a waveform of high value when the trigger pulse goes low. So this is all about monostable multivibrator circuit by using 555 timer. I have in this particular lecture discussed about the operation, how the circuit works, and then I have shown you the different waveforms, and then lastly determine or find the value of this TW and have a talk how to implement this particular circuit in practical. So, goodbye.